Hi, my name is Steve Denenberg. Let's get something written here. This is the first of a series of videos where I will explain and discuss concepts of physics, hopefully in a way that makes understanding and using those concepts easy, exactly how I tutor my kids. I will cover much of what is covered in AP Physics 1, and we will do problems from past AP exams to show how straightforward they can be. Any errors are my fault. I welcome suggestions of how to make the presentations more effective. So let's get started. In this talk, we are going to talk about the equation d equals 1/2 at squared, which is an elementary equation that you encounter that talks about how a body, a particle's position changes with time under a uniform acceleration. Now, we're assuming certain things. We're assuming that you know what d is, what the distance is. Distance is your position. If we have an x-axis here, where are you? What is your position? And it's measured in meters. That's the standard unit. Your velocity is meters per second. It's how your position is changing with time. If your position is changing very rapidly with time, you have a high velocity, right? And acceleration is the change in velocity with time. It's how your velocity is changing. Are you starting out slow and then getting faster? And acceleration, being the change in velocity with time, is meters per second, which is your velocity, per second. And that's meters per second squared. So if you're accelerating at 4 meters per second squared, that means every second your velocity is changing by 4 meters per second. And we're going to figure out what that does to your position, because your velocity is not constant, it's changing. So just simply, let's say you're on the edge of a building and you drop a ball off the edge of the building and it's heading down under the pull of gravity. Gravity is an acceleration, and we'll talk more about that. But so here's our acceleration. And what is the position of this ball as it drops under the acceleration of gravity? Well, its distance from where you left it is 1/2 times a times t squared. So let's put some numbers in that. Let's say that the acceleration of gravity equals 10 meters per second squared. So your distance after 1 second is 1/2 times 10 times 1 squared. And that'll be 5 meters. In 1 second, this ball is going to drop by 5 meters. Now, talking about units, let's make sure our units are okay. Let's do a units calculation of this equation here. We're going to say d, which is in meters, is 1/2 times a, and a is in meters per second squared, times t squared. And t squared is seconds squared. Because we have, if t is squared, we have seconds squared there. So on the right side of this equation, we have seconds squared in the denominator and seconds squared in the numerator, and those cancel. And all we're left with units-wise is meters. And sure enough, the units here work out. So what's happening now is that this ball, as it falls, is accelerating. So after 2 seconds, it's fallen 1/2 times a times 2 squared. So compared to how far it falls in 1 second, it's fallen 4 times as far. And then in 3 seconds, it's traveled 1/2 times 10 times 3 squared meters. So it travels 9 times farther in 3 seconds than it did in 1 second. And we're going to use that to figure out what the total distance is. Okay, so let's take a look at where this equation came from, this d equals 1/2 at squared. Okay, and we're going to take a look at a couple of charts. So if something is traveling at 5 meters per second, and it's traveling for 8 seconds, we know that the distance that something travels is the speed, is the speed at which it travels times the time it's been traveling. If it travels a high speed, it's going to be a high distance. If it travels a high time, it's going to be a high distance, okay? And here's where we can look at some charts, because charts are going to be important. If we have a chart that shows time here and distance traveled here, then if something has a constant velocity, it's going to travel farther and farther and farther with time, right? But let's take something that is dropping off the edge of a cliff. Something that's dropping like that, let's plot its velocity against time. With a constant acceleration, okay, its velocity is going to go up and up and up and up. Okay? Now, so this is the velocity time graph, okay? And what is the slope of that line? Well, we know from basic charting that if we have an equation y equals mx plus b, that's the equation of a line, and m is the slope of the line, okay? Here we have t on the x-axis and v on the y-axis. So we have v, the velocity of something, is the acceleration multiplied by the time. The velocity increases every second according to how fast it's accelerating, okay? So if v equals at, this looks like y equals mx, and the slope of this line equals a. If you have a constant acceleration, the velocity against time graph has a slope of the acceleration. So let's write that down. Now, what is curious about the velocity versus time graph is that the area underneath the velocity versus time graph, this area here, this tells us how far something has gone. Now, why is that? If you have a box that is a certain height and a certain width, and you want to know the area of the box, okay, you multiply the height times the width, and that gets you the area. So an h times w is the area that is enclosed like that, okay? If you have something traveling a certain distance for a certain amount of time, how far did it go? Well, let's make a box out of it. Let's say that, can I do that? Let's say that this is how long it's been traveling, and this is its velocity. So distance, as we know, equals velocity times time. How fast it's going for how long is the distance. Well, v times t is going to be a box that has v height and t width. Does that make sense? So what we're learning here is that the area of the velocity versus time gives us how far something has traveled. So if we go back up here to this little graph here, when the particle takes off, it's starting out at a low time. It has a low velocity. The velocity is the y-axis. And it speeds up, and it speeds up, and it speeds up. In this little piece of time right here, it's traveled a bigger distance because it already has a higher velocity, okay? So if we've learned from down here that the area under the velocity versus time graph is the distance something has traveled, what is the area what is the area that we've marked in here? Well, this is a triangle that has t for its base and v for its height, okay? And it has a slope of a, okay? So after it's traveled for a certain time t, its velocity is going to be t times a, right? Didn't we figure that out? The velocity is the acceleration times the amount of time. So this distance here is t times a, and this distance here is t. Well, what's the area of a triangle? It's the base times the height, which here is t times a times t divided by 1/2 times 1/2. And that equals 1/2 a t squared. So this is where we get that the distance traveled by an object under a constant acceleration for a certain amount of time, it's going to travel 1/2 at squared. That's the distance. Okay? So now let's do a little bit more exploration of that. Let's ask a different question. We drop a ball off a building, okay, and it falls to the ground, and it hits the ground, and it has fallen a certain distance. How long did it take to get there? Okay, well, let's see. We have d equals 1/2 a t squared. But we want to find out how long it took to get there. We want to know what the time is. Well, here's our 8th grade algebra. Let's multiply both sides by 2. 2d equals at squared. And I'm always telling people, don't do this whole thing in one step. Do it a tiny piece at a time, and that way you won't make mistakes. Just do it tiny pieces at a time. Divide both sides by a. 2d over a equals t squared. And now let's take the square root of both sides. So t equals the square root of 2d over a. And that's how long it took for this ball to fall a distance d. So now you're able to get the time. Now, once again, let's do a units calculation, see if we got that right. T equals seconds, okay? D equals meters. A is meters per second squared. So that's meters per second squared, okay? So the m's cancel out. The top and the bottom can be multiplied by seconds squared. And the square root of seconds squared equals seconds. See, so that works. You don't really have to do this, just you have to understand it. Right, but now we've been able to find out what the time is. Okay, now let's go back to the same problem. A ball drops a certain distance d and it hits the ground. What is its speed when it hits the ground? Do we know what the speed is? Well, sure. We know what a speed is because it's falling under a constant acceleration. And the speed of a particle equals the acceleration times the time that it's been falling. And now we know what the time is. So the speed when it hits equals its acceleration times the time, which equals a times the square root of 2d over a. Let's figure this out one step at a time. That'll keep you from getting in trouble at the physics test. That's the square root of a squared over 1 times the square root of 2d over a, and that's the square root of 2d a squared over a, and that's the square root of 2d a. Okay, so that's the speed at which the particle hits. And when we take a look at energy, we'll have an even easier way of doing it. Okay, so now we know if something has been falling for a certain amount of time, we can figure out how far it fell. We can figure out how long it took to fall that distance, and we can figure out the speed at which it hit.